Hello, everybody. I am back, and we are going to get started with Chapter 8, which is all about a new group of biomolecules. This is about lipids. So, you've probably heard of lipids before, right? Again, pretty common topic that pops up in various biology classes. Lipids are an essential biomolecule. We have more uses and more types of lipids in the body than you ever could appreciate. It's pretty impressive. We're going to learn a little bit about the basic nature of lipids, and then also we're going to get in and talk about several of the different types that we have and their structural features. That's going to be sort of the first half and kind of the first video I'm going to make with this chapter. And then the second half of the chapter deals a little bit more with specifically their use of membranes. Just a heads up, this chapter is pretty organic chemistry heavy. And so I'll be referring to a lot of just common structural features and aspects that are typically learned in organic chemistry. If you feel that you need a refresher on some of these, or if you haven't heard of some of these before, please let me know. I'm going to try to sort of go over these step by step in the recording here. But if I miss anything, or if you need to brush up on something, just let me know. I'll be happy to help you out. All right. So, what are lipids? It's kind of funny if you look up the definition of the word lipid in the dictionary. It's terrible. It's very vague, and it's really not very accurate at all. Sorry, I'm yawning. Must be boring myself. Basically, there's really not a good definition for lipids because they're pretty diverse molecules. There's actually lots of different types of lipids that you can have with not only different purposes, but also a fairly wide array of structural features. However, there are certain structural features that most of these are going to have in common. One thing is that the structures typically have a lot of prominent hydrophobic areas, right? We've talked a little bit about fatty acids before, right? Remember in one of the earlier chapters I talked to you guys about making soap, right? And we talked about how fatty acids are, and I'll skip ahead here, you can see the magic word here, amphipathic. These amphipathic compounds that have both hydrophobic and hydrophilic regions. Well, those hydrophobic regions are really commonly found in a number of different lipids, not just fatty acids. So they're usually not soluble in water. There's a couple of different broad categories. Number one is the one that the fatty acids fall into, and actually this is the group that will have the most individual subtypes of lipids. I swear I did not start yawning until I started talking, so I don't know what's up with that. Sorry about that. That first group is going to be lipids that have, in addition to these hydrophobic regions, tails, they also have polar portions, right? Some polar head group, at least one polar head group, sometimes more. And then there's a separate group that instead of having these long alkane-like tails in polar head groups, they tend to be more ring systems. They'll have lots of rings, usually a lot of them fused together, very, very rigid structure. So we'll take a look at each group as we get to them. All right, so we're going to start off with the first group, the polar head group, nonpolar tail, and we're going to revisit something that's kind of familiar to us already, right? Fatty acids. And I talked about this previously. Just to refresh you, a fatty acid is going to be something that has a polar head group and a hydrophobic tail. So, something like this. This would be a good example of a fatty acid. Polar head group, hydrophobic tail. So, just like we said last time, a good example of what we call an amphipathic compound. Let's dig a little deeper into fatty acids, though, and take a closer look at both at the different structural features that we can find in them. And I want to pay special attention to the hydrocarbon tail. That's going to be the biggest thing to look at. All right. One thing that you can notice when I drew this, and this is just a sample one, but this is very representative of the nature of the hydrophobic tails. They tend to be very linear. You don't usually see branching of any kind, right? And even if you do, it's usually a very small branch, like maybe a methyl group or something. These tend to be very, very linear chains. All right. Also, one thing to keep in mind when you look at fatty acids is it's going to be important to count your carbons. And I'll give you a little bit of bookkeeping nomenclature in just a minute. But one thing that you'll notice is that almost always they tend to contain an even number of carbons. They'll usually contain anywhere from about 12 to 20 or so. Those are the most common ones, and there are some outliers that have them a little bit longer. The one I drew in the previous example on the whiteboard had 12, right? They may or may not contain double bonds. All right, this one did not contain any double bonds, right? Just straight chain alkane. There's a term that we use for fatty acids that have 0 double bonds in their tails, and that is called a saturated fatty acid. If something's got a double bond, at least one double bond in there, right? Let's say we just stuck one right there. That adds 1 degree of what we call unsaturation. By the way, the term saturated, when you talk about saturated tail, I'll just use this as an example. Basically, that means all these carbons, 6 carbons here that I've circled, when they're in a chain like this, the maximum number of hydrogens they could ever hold would be 18. No, excuse me, sorry. 13. 3 here. 2 here. 2 here. 2 here. 2 here. And 2 here. 2, 4, 6, 8, 10, 13. All right? So when these 6 carbons are laid out in a carbon chain like this is the most hydrogens they could ever hold, right? Because their other bonds are being used up, being attached to other carbons, right? Well, when you introduce a double bond, a pi bond, let's say we introduce one right here, right? Those 6 carbons don't have the maximum possible number of H's that they could hold anymore, because we've introduced this double bond right here. That means these 2 carbons each can only hold 1 hydrogen, right? That reduces the number of possible hydrogens held by these carbons, in this case by 2. That's called we've added what we call a degree of unsaturation. Basically, a degree of unsaturation adds a pi bond and takes away 2 hydrogens, right? And that's what we've done over here. We've introduced 1 pi bond, all right? So this one is unsaturated. All right? Now, things get a little bit more complex with unsaturated. First of all, you can have more than 1 double bond. You can have more than 1 pi bond present. All right, in this example, I'm going to introduce a term And probably several of these terms are ones that you guys have heard of before, especially in talks of health and nutrition. This is what we call a monounsaturated fat because it has 1 degree of unsaturation. You can have more. Let's say we had one here, but also over here. Right? In this case, we have 2 degrees of unsaturation. If it has 2 or more, it's called a polyunsaturated fat or polyunsaturated fatty acid. Polyunsaturated fat is just, or saturated fat, etc. Those are shorthand ways of saying fatty acids. All right? All right. Not done with the unsaturated ones yet. I'll draw a couple more. All right, let's draw this one. This is the one I just drew before. And then let's compare it to this one. All right. So, how are these different? They both have the same number of carbons, right? They both have 12. They both have the double bond being introduced at the same point, right? 1, 2, 3, 4, 5, 6, 7. Carbon number 7 is the first one that has it on the top, and 1, 2, 3, 4, 5, 6, 7. Carbon number 7 is the one that has it in the bottom. What's the only difference? If you guess stereochemistry, you are correct, right? Remember, when you have double bonds, you can have different stereochemical arrangements, right? Remember talking about cis and trans, right? In the top one, we have what we call a trans arrangement because the 2 groups on the carbons and the double bonds are pointed in opposite directions. So this is a trans fatty acid. The one on the bottom, the 2 groups on the carbons and the double bond are pointed in the same direction, so that is a cis fatty acid. All right? So, each of these would be monounsaturated. One would be a monounsaturated trans fat, one would be a monounsaturated cis fat. And again, you've probably heard some of these terms before, especially like food labels, nutrition, etc. I'm going to come back to that in just a minute. So sort of put these terms in your back pocket. I'm going to revisit them in a little bit. All right. There's lots of different types of fatty acids. There's a picture, as always, give you the disclaimer. PowerPoint it's cutting off my pictures here, so be sure to look in your book or on the computer for your PowerPoint. But here's an example of several common ones. Palmitic acid, stearic acid, oleic, linoleic, alpha-linolenic, and arachidonic acid. And you can see these all kind of have the same basic, layout, polar head group, hydrocarbon tail, but you're either going to differ in the number of carbons that are present in the chain, the number of double bonds in the chain, and or the cis-trans arrangement, right? So these are really common. Fatty acids are really common, of course, in foods and also in cosmetics as well. So pick up a nutrition label sometime or look at the ingredient list on your shampoo or something. You'll probably find some of these fatty acids that are in this picture in your ingredient list. All right. All right, so I want to introduce you now to a little bit of some more terminology / bookkeeping notation, whatever. Okay. So let's see, let me think here. I'm counting carbon, so give me a second. I'm going to draw the 16 carbon fatty acid unsaturated. So that's 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So this is palmitic acid. All right. It's got 16 carbons and no double bonds, right? So there's a bit of shorthand terminology that you can use to represent this to a reader or somebody else, that needs the information, to tell them, hey, this is the one we got, right? So it's not uncommon to see palmitic acid referred to as having this notation, 16:0. All right? This number here refers to the number of carbons in the chain. All right? So, and that means the entire molecule, including the carbonyl carbon, right? So including that one, we have a total of 16. All right? This over here refers to the number of pi bonds. So, if you see something has 16:0, that means it's the 16 carbon fatty acid, no pi bonds, no double bonds. All right? Let's change it a little bit. I'm going to put a double bond in 2, 3, 4, 5. Starting at, let me count, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right here. Okay. This is called palmitoleic acid. Palmitoleic acid, there you go. These become tongue twisters at various points. All right, and we would write this one this way. There's a couple of different ways you could write this. You could write it like this, and this is not incorrect, right? It's just the same way that we just wrote it. It tells you there's 16 carbons and there's one double bond. However, it's not fully descriptive because it doesn't tell you where that double bond is. All right? So we can make a little addition. Put a little dash in, and then you put a delta sign. And then on the delta sign, you put a little superscript, in this case a 9. This tells you where the double bond is. It's the first carbon where the double bond appears. So in palmitoleic acid, it's 16 carbons long, counting the carbons, starting with carbon number 1, the carbonyl carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where the double bond appears. So you put it there. Okay? Hypothetically, and this would not be palmitoleic acid anymore, so I'm going to cross that out. Let's say we had another one right here. So, again, it's still 16 carbons, right? But now we have 2 double bonds, so it's going to be 16:2. And we got to tell you where they are. We still have one at number 9. We have another one, so you put a comma. And then the second one appears at carbon number, 10, 11, 12. So it'd be 16:2, delta 9, comma 12. So just a little bit of bookkeeping to help you recognize the general features of your fatty acid. All right, so I'll show you a couple of tables here because I want to relate the structural features of fatty acids to a certain physical property, and it's going to be melting point, right? Remember, in organic, we talked about melting point, right, and the various things that can affect melting point. Of course, intermolecular forces were important: hydrogen bonds, dipole-dipole interactions, van der Waals, right? And we're going to see that play out here with lipids. All right. So this is a table. These are all, by the way, these are all unsaturated fatty acids, right? Lauric, myristic, palmitic, stearic, and arachidic. These are all unsaturated, no double bonds. The only difference between them structurally is the number of carbons, right? If you'll notice, what happens to the melting point as the number of carbons goes up? You see the melting point gets higher. And that falls right in with what you learned in OChem. All right, so like for example, let's say we drew lauric acid. It's got 12. All right. Then let's say I compared it to palmitic, which has 16. All right. So they look exactly the same. The only difference is the fact that palmitic has 4 extra carbons. All right. So which one has the longer chain? Obviously, it's palmitic, right? Well, one of the things that we learned in organic chemistry was that the more surface area you have in a molecule, the more opportunities for van der Waals forces, right? So you could have 2 palmitic acids kind of interacting with each other. I don't know if I drew the right number of carbons or not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. Right? And so you see, you have this big, large area here where you have these both hydrophobic tails sort of interacting with each other. They're interacting through van der Waals forces. And these van der Waals forces act as sort of like, a weak little glue that holds them together. Same thing for lauric acid up here. Sorry. Let's move that out of the way. You have this region where you have van der Waals interactions. Common sense should tell you that the longer the chain, the more of these van der Waals interactions that you have. The more van der Waals interactions that you have, the stronger the attraction, and the more they're going to stick to each other. The stronger they stick to each other, the more energy that's needed to break them apart, right? So, palmitic, for those reasons, is going to have a higher melting point. Just because of the accumulation of these interactions. All right? That's not the only factor, though, that's important in melting point in fatty acids. All right, I'm going to show you another table. Table 8.2. All right, and so this one shows you a series of another 5 acids, palmitoleic, oleic, linoleic, linolenic, and arachidonic acid. All right, and as you can see, it increases from 16 to 18. Then you have a couple of others that have 18, and then arachidonic has 20. Now, look at the melting points. Do you see the same linear increase in melting point that we saw with the previous 5 acids? The answer is no, right? That's because we're introducing a new factor here. Here we're introducing degrees of unsaturation. We're introducing double bonds. All right, look at that table. Now look at the column that says degree of unsaturation. With palmitoleic, we have 1. With oleic, we have 1. With linolenic, we have 2. Linoleic, we have 2. Linolenic, we have 3. And arachidonic, we have 4. Right? Do you see any trends here? What happens to the melting point as you increase the number of pi bonds? You see it go down, right? Yeah, increase pi bonds, lower the melting point. So you can even see here, so something like arachidonic acid, it has the longest carbon chain of 20. It has a lower melting point than even palmitoleic that has 4 fewer carbon atoms, right? So what's happening here? Well, I want to go back to a photo. One second. This slide here that says common fatty acids. All right, so look through some of these. All right, so remember when I told you about a couple of different conformations, stereochemical conformations you could have. You introduce a pi bond, you can have a trans fatty acid, or you can have a cis, right? Well, something funny happens when you have cis fatty acids. When you have cis fatty acids, it sort of introduces a weird little shape in the chain. It's not so straight anymore. It introduces like a little kink, a little turn, right? So you see it a little bit with oleic acid, and it's 1 double bond. But if you look at linoleic acid, and it's 2 double bonds, you see it's more pronounced. If you look at arachidonic acid and it's 4, you see it's very pronounced, right? So the more cis double bonds that you have in your chain, the more awkward and erratically shaped the chains are. Now, whoops. You get the most optimal interactions of van der Waals when they can get really close together. I'm just drawing a random sample here. This isn't a real fatty acid. And boy, howdy, did I do a sloppy job of drawing it. Sorry about that. But the point is that you get the maximum interaction of van der Waals when they can really kind of stack together like dinner plates, right? These two chains are very regularly shaped, and they can sort of fit together literally like dinner plates or puzzle pieces or something. They can get very close to each other, and that means the van der Waals forces are optimized. Whereas if you have something like this, right? Imagine trying to have 2 of these tails fit together. It's very hard to get them to line up, right? So they still interact, but at a larger distance from each other. The more distance that's between the tails, the weaker the interactions, and therefore the less energy it takes to break them apart, right? So more double bonds equals more opportunity for cis double bonds, which gives you kinks in the chain. They don't fit together as well. Takes less energy to break them apart, so that's why you have a lower melting point. It also makes you understand some basic nutrition, right? Oh shoot, sorry, I didn't mean to do that. Go back to the whiteboard. So I told you I was going to come back to this. So you've heard of trans fats, you've heard of cis fats, you've heard of saturated fats, you've heard of unsaturated, and within that you've heard of monounsaturated and polyunsaturated. and you've heard this in nutrition. You can see a lot of these on nutrition labels. You know that some of them are good for you, are supposed to be good for you, and some of them are bad for you. And really, that's more in terms of heart health, right? Here's one. All right. Again, let's say you have a saturated fat. All right. Think for a second. Are saturated fats supposed to be good or bad for you? All right. Da 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 da. Drum roll. They're supposed to be not as good for you. They're kind of bad. I'm not saying you're gonna, keel over if you eat a saturated fat, but accumulation of them is not very good in your bloodstream because again, they can stack together like dinner plates, right? You have a lot of interaction here, and that increases the melting point. The higher the melting point, the more solid-like behavior they have, at your biological temperature, 98.6 degrees, or give or take. All right? Think about your bloodstream. Think about your arteries. Fatty acids and related compounds are being transported through your blood all the time. All right? There's actually a complex process for doing that. This is not the time or the place for it. I usually, in the past, when I talked about it in biochem too. I don't know if I'll get to that or not. But in a nutshell, these compounds are being transported all the time in your bloodstream. All right? Let's say you have a bunch of them that are being carried together, right? Let's say you have a bunch of them that are saturated. They can pack tight together in very dense structures and make something that has a high melting point. That means you have these fatty acid masses acting as solids in your bloodstream. That's not good, because when you have solid-like structures in your bloodstream, that causes blockages. And that means things, namely blood and whatever is in the blood, cannot flow back and forth. All right? That's bad. We want the fats in our bloodstream to have low melting points so they'll be in liquid form and they can flow freely instead of causing these blockages. Right? All right, so saturated fats, bad. How about cis and trans fats? Well, let me show you a trans fat. All right. There's a trans fat. Ran out of room here, sorry. My OH is sloppy. Ugh. What can you tell me about trans fats and their interactions? Looks kind of like saturated fats, right? Yeah. Due to the shape, the consistent zigzag structure of these, they don't fit, or they fit together very, very well. So, trans fats are bad. In fact, I think some studies have shown trans fats are actually worse for you in a lot of cases than saturated fats even. So that's why when you see something advertised that it has no trans fats, they're trying to get that across. All right? How about cis fats? Well, hold on, I'm going to pause. Sorry for that. My family just delivered me a fan from my office, which is great because it's kind of hot in here, so I really appreciate it. So, sorry for the pause there. Okay, so let's say we have something like that. Um, I know these don't have the same number of carbons in them. I don't care because it doesn't really matter. All right. So when we have these cis double bonds, this, like I said, this introduces some irregularity to the chains, right? It introduces these little kinks. That means they can't fit together as well, right? So cis fatty acids tend to have lower melting points. And that's good, right? Yeah, cis fatty acids. And the more cis fatty acids, or excuse me, the more cis groups that we have, the better. So, if you're comparing monounsaturated and poly, they both can be what we call good fats, but poly is always better. Because the more areas of unsaturation, the more chances you have for cis arrangements, less interaction, lower melting point. So, a good example of this is, have you ever seen in the stores, you can get margarine in different types. Margarine has a bunch of fatty acids in it. There's different types you can get. You can get the hard compressed sticks, right, that you slice off with a knife. You can get kind of a softer margarine, like usually in a tub or something, that's still mostly solid, but is a little softer and is a little bit easier to spread. And then you also have that spray margarine, right? It's in the refrigerated section, but it's still completely liquid, and you literally just spray it onto your bread or whatever you're doing. Well, there's going to be direct differences amongst those three groups in a number of saturated fats and possibly trans fats as well that are present in each one, right? The one that's a stick is going to have the most solid-like character, and it's going to be harder to melt. Whereas the spray butter, even at refrigerated temperatures, it's still a liquid and flows freely. So if you're looking, for heart-healthy margarine, the best one to get is the one in the spray bottle, because it's going to have much less of a tendency to make these solid masses. One other little thing, and by the way, I'm spending a sort of an absorbent amount of time on fatty acids just because they're interesting and there's lots of really good, I guess, real world examples. I'm not going to spend this much time on the other ones. There's going to be a little bit more quick hitting, but a lot of the stuff that we're seeing here with fatty acids can also resonate with the other lipids as well. All right. One last thing to highlight, it's kind of interesting. And this ties together with something you learned in organic chemistry. So, a lot of times if you look at the back of, margarine, peanut butter, mayonnaise, something with a lot of fat in it, you might see on the ingredient list partially hydrogenated oil. I don't know if you've ever seen that, or if you have, if you ever really thought about it. But it's an interesting bit of marketing lingo that's used. All right? I'm going to throw you back to organic chemistry a little bit here. So let's say we had... let's say we have an alkene. All right? One of the things that you can do with an alkene is you can do what we call a catalytic hydrogenation. And so what you do is you take some H2 and a metal catalyst like palladium or something like that, and an H gets added to each one of the carbons on your double bond. So if you're looking at the two carbons that used to be in a double bond, there they are, and here's the two H's that we just stuck on them, right? So you see, in this case, we went from an alkene to an alkane, and this process removed one side of unsaturation, right? That happens in the food industry, right? So a lot of times you can get certain types of oils, especially vegetable oils, that have lots of different areas of unsaturation. In other words, it has several double bonds in its tail, right? Which is a good thing nutritionally. And what they do is they take some of these double bonds and they hydrogenate them. And so they remove areas of unsaturated. In a nutshell, what this process does is it makes your fatty acid more saturated than it would have been otherwise. So, it's just something, it's a sort of a weasel term. It is not favorable, marketing-wise, a lot of times, to list that you have a saturated fat, right? Technically speaking, if you start off with an unsaturated fat, but then hydrogenate it to make it saturated, you don't have to write saturated fat. You just write partially hydrogenated oil. All right, so it's really very much a weasel term there for marketing, but it is what it is. So just keep that in mind. If you see partially hydrogenated oil on your nutrition label, that's what it's referring to. It's making the original ingredients more saturated than they would have been otherwise. All right. Let's move on to some other ones here. So, this one also is going to be one that you've probably heard of, even if you don't necessarily realize that you have. This is triacylglycerols. If you haven't heard of the term triacylglycerol, you might have heard the term triglyceride before. That's a term that's used commonly, like when you do cholesterol testing. Triglycerides are not cholesterol, but that's just another. When I do cholesterol testing, they'll also test the levels of these guys, triglycerides or triacylglycerols. All right. So basically, these are derivatives of the molecule glycerol. Glycerol is this little guy right here. It's a triol. It's got 3 alcohol groups. All right, 3 reactive alcohol groups, so there's a lot you can do with glycerol. One of the most important things that glycerol can be involved in is storage of fatty acids. All right, if you take a molecule of glycerol and you add a fatty acid, I'm just going to use R group here for the hydrophobic tail. It can form an ester linkage. And it gives off water as a side product. Each glycerol can hold 3 fatty acids. And this is how the primary way in which organisms store fatty acids, right? So if you're wondering what fat cells are made out of, fat cells have a whole lot of triacylglycerols. Sorry, I'm trying to find my button, home button. There it is. Yeah, so triacylglycerols are primarily found in adipose tissue, fat cells, and they if you have excess fatty acids, they are esterified to glycerol, and they sort of sit there until they're needed, right? If they are needed, they're usually converted. This ester bond is broken down enzymatically. Right, and the class of enzymes that are used to break these ester linkages are called lipases, specifically for breakdown of ester linkages involving fatty acids. All right, so Whenever you do this, you can free anywhere from 1 to 3 of these fatty acids, um, and they are released in the form of ionized fatty acids, so they're negatively charged on the head group. And glycerol is regenerated. Fun fact, you don't have to have an enzyme to do this. Well, you do in the body, but outside the body, on a lab bench or something, you can do this with aqueous NaOH. Guess what? Remember when I told you how they used to make soap? Right? They would get the animal fats and put lye in it. Lye is NaOH. That's what they were doing. They were doing a process called saponification. Saponification is just a fancy term for base-catalyzed hydrolysis of an ester, right? So the only difference is when you do it this way, it releases the ionized fatty acids, but you also have sodium left over from the sodium hydroxide, and they make a salt. Fun fact, if you have hard water in your home, you've ever had hard water in your home and you finish taking a shower or bath or something, and you end up with, I guess generally it's called soap scum, that kind of sort of slick coating that's left over on the bathtub, and sometimes your skin, I suppose. It's hard to rinse off. That is actually the same thing. You basically have leftover salts of these fatty acids that are present in whatever soap that you're using. Hard water has a lot of magnesium and calcium in it, and so what happens is the magnesium and calcium ions form salts with the fatty acids that might be present in your soap. Magnesium salts and calcium salts are not so water soluble like sodium salts are, so that's why it's hard to get rid of. Little something to think of next time you have soap scum in your tub. All right, let's take a breath, deep breath. Those aren't too bad, right? Those are pretty easy. We're about to head into sort of a gauntlet of biomolecules here, and so I'm going to highlight a lot of structural features here in a short amount of time. Just take them one at a time. You'll see actually a lot of them are kind of common to each other. But not going to lie to you, this part's a little bit tedious. Because we have several other important lipids that we can look at. Right, a lot of these have subcategories. First one that we're going to be looking at is something called a phosphoacylglycerol. All right, so let's just say that you had glycerol, right? You know, it's got 3 OH groups. Let's say that one of them made an ester linkage not with a fatty acid, but with phosphoric acid. Something like that. That guy is called phosphatidic acid. And you can see it represented over here on the left-hand side. Actually, let me back up. Let me correct myself. Phosphatidic acid actually wouldn't have 2 other OHs. It would have 2 other fatty acids attached. So this is phosphatidic acid. Sorry about that. All right, so you have phosphatidic acid. That's sort of a root compound where you can make several different types of what we call phosphoacylglycerols. And which type of phosphoacylglycerol do you have? Well, it all depends on what else you might have attached to this guy down here, right? You can have other stuff coming off of this. The identity of this R group will tell you what type of phosphoacylglycerol that you have. Alright, so let's just take a look at a few of them. One thing in general about phosphoacylglycerols is that you're going to see a lot of them that are found in biological membranes, right? This includes cell membranes, this includes nuclear membranes, this includes larger. This includes larger membranes that are more like tissue membranes. They have large amounts of lipids in them, and a large percentage of these lipids are phospholipids or phosphoacylglycerols. All right, some of the specific ones. There's one called phosphatidylcholine. All right, and again, if you look at the complete picture of this in the PowerPoint, you can see the structure. All right, so phosphatidylcholines, a couple of things about them is the two fatty acid ester linkages, they kind of bind together to form, rewind that last part. I was looking at it wrong. All right, so the unique part of this one is not the fatty acid esters, but the group that's on the very end of the phosphate, right? You see the OCH2CH2 positive end with three methyls. That tail is called choline. And when choline is bound to that phosphate group, that's called phosphatidylcholine. So, one of the most common places that you can find phosphatidylcholine is in egg yolks. Yeah, egg yolks. Very, very good for you. Egg yolks, soybeans. There's various types of phosphatidylcholine. You can have phosphatidylcholine derivatives. Just want to highlight one of them. Lecithin, again, you can find lecithin in large amounts in egg yolks, quite a bit. But also, this is found actually naturally in the body as what we call a pulmonary surfactant. In your lungs, down deep in your alveoli, these are actually coated with sort of these mucous membranes, and part of this is going to be lecithin, which is a pulmonary surfactant. Pulmonary surfactant basically acts to kind of help keep the alveolar sacs from sort of collapsing in on themselves. They sort of act as sort of repellents to keep the individual walls from touching each other. All right. Very important, because otherwise, if we didn't have this, our lungs would collapse at a moment's notice. All right. The other ones aren't in the PowerPoint, but they are in your book. I'll just highlight them real quick. We have one called phosphatidylethanolamine, also called cephalin, if you don't like the longer name. All right, so if you look at the tail end of this is the part that's connected to your phosphorus. That's the ethanolamine tail. And again, just like any other phospholipid, is found in high concentrations in membranes, but specifically, this one's found quite a bit in the nervous system. So, important membrane lipid for nervous system cells. All right, we got another one, phosphatidylserine. Ooh, that should give you a hint as to what's on this. Yeah, this one has a serine attached to your phosphorus. I drew this. I drew this incorrectly in my notes. How embarrassing. Oh, that should be a C. One second. Yeah. So this is a case where you have a serine residue that's attached to your phosphorus. Um, Specifically, this one's in the cell membrane quite a bit. It's in some other membranes as well, but the cell membrane is probably going to have its precedence more than others. This one's also used in various, I don't know why I spelled cell with an I. I'm really losing it today. It's involved in what we call cell signaling. All right, and so basically, this particular lipid can sort of act as an intracellular signal to trigger some sort of cellular mechanism or process. And one in particular that it's involved in signaling is apoptosis, which is a type of programmed cell destruction or death. So it's kind of like, in that case, a suicide lipid for the cell. All right, a couple more of these. Phosphatidylglycerol has, what do you think it has on it? Wait for it, wait for it. Yeah, glycerol. It's got another glycerol attached at the phosphorus. This one's also present in pulmonary surfactant. Wow, that looks terrible. I'm not a good writer anyway, but man, it's worse on a tablet. Also, this is an important lipid in activation of something that we call lipid-gated ion channels. Wow, that sounds fancy, doesn't it? So basically, as you go in and across, in and out of various membranes, membrane chambers like the cell and nucleus, you have to have little channels that you can get through, right? And so there are certain of these channels that are called what we call lipid-gated channels. In other words, these gates, quote unquote, are opened or closed by the presence of certain lipids, right? Phosphatidylglycerol can act as a sort of a guard, I guess you could say, if we're using a metaphor here, for these channels. And specifically, these are channels to let certain types of ions in and out of the guarded chambers. And then we have one more that I'm going to highlight. That is phosphatidyl inositol. Right? What the heck is inositol? Inositol is a type of sugar. It's a simple sugar. So, let me draw it here. It's going to look a little different. We haven't gone over sugars yet. That's going to be the next chapter. So I'll just draw it for you to see. There's a certain way that we draw sugars. I'm running out of space big time here. By the way, this picture's in your book too, so probably looks a lot better. Okay, so basically it's got this phosphatidyl inositol has this particular inositol sugar that's bonded to your phosphorus. This one much like phosphatidylserine is involved in signaling, although it's a little bit more versatile. This is involved in not only cell signaling, but other types of signaling in different metabolic pathways in the body. All right. So those are the phosphoacylglycerols. We can talk a little bit about waxes. Waxes are a really, really generic, or I won't say generic, broad group of compounds because there's lots of different types. Basically, waxes are going to be, here's an example here of, sorry, I'm trying to find the photo and want the picture in my book because I want to see the whole photo. Here's a couple of examples of common waxes. Myrcel ceretate and cetyl palmitate. So really, these are just fatty acid esters where that polar head group has been esterified to some other longer chain. And so basically, these are really, really freaking long chains that have a carboxy group in the middle of them. Right? And you can see, count the number of carbons there, just see how long they are. They can be found in a lot of different places. Carnauba wax, used to wax your car, is one. That one has a lot of myrcel ceretate in it. I mentioned spermaceti. You ever seen a sperm whale? It's like the whale in Moby Dick, the ones that have the really big heads. Those heads are filled with a wax, cetyl palmitate. And what it does, it actually helps to regulate its diving and depth position in the ocean. Sperm whales were actually hunted quite a bit many centuries ago. Since then, they've put in a lot of protections for them, so they're not so much anymore. But they used to be hunted because people wanted to get that wax out of their head, for lack of a better term. The wax was mostly composed of cetyl palmitate, but the general term that was used for the overall composition is called spermaceti. So, and then spermaceti can be harvested from whales. You can make candles out of it. You can use it to fuel lanterns, a lot of heating and lighting purposes. Now, of course, not only do we have better ways of heating and lighting, but these animals are protected. So, all right. Sphingolipids. All right, so sphingolipids, it all starts with something, these are all much like phosphoacylglycerols were derived from phosphatidic acid. Sphingolipids are derived from something called sphingosine. And if you look in this photo, you can see sphingosine. Basically, sphingosine is going to have a couple of free hydroxy groups, right? A couple of free OHs. It's going to have some sort of hydrophobic tail on the top, carbon that's double bonded, and then it's got an NH2 group on one of the middle C's, right? Sphingosine is referred to as an amino alcohol because it has both amino groups and alcohol groups in it. All right, so that's sphingosine. And depending on how you derive that molecule into something else, it'll give you a different type of sphingolipid. All right. So, what can you get? Probably one of the most important types of sphingolipids that you can get is something called a ceramide. And again, you may have heard of ceramides in like cosmetics or lotions, moisturizers, right? Ceramides are sphingosines that have had an amide linkage formed at their amino group. And this is going to come from a fatty acid, right? So, if you look at this photo right here, take a look at that CHNH2, it's going to react with a fatty acid, and fatty acid plus amine is going to make an amide, a secondary amide. Kind of like a peptide bond, actually, right? Then you can have different types of ceramides as well. Probably one of the most important types is one called sphingomyelin. And hey, you've probably heard of this in a biology class. Where do you find sphingomyelin? You find it in the nervous system, right? Have you ever heard of something called the myelin sheath? Right? Myelin sheath is this protective coating that you see in nerve cells to basically sort of help it continue to conduct nerve impulses. Well, this myelin sheath in large part is composed of this lipid, sphingomyelin. Right? In sphingomyelin, you basically have a ceramide where that primary alcohol group at the end has been you've had a phosphoric acid ester linked to it, and then a molecule called choline attached at the very end of it. Very, very important molecule in the operation of our nervous system. All right. The last broad group in this category is glycolipids. All right. Glycolipids, the unique thing about glycolipids is that they have sugars, right? Sugars or saccharides. Saccharide is another term for sugars. The term sugar, saccharide, and carbohydrate are all interchangeable. They all mean the same thing. All right. So what happens in glycolipids is that you have a lipid that is bonded to a hydroxyl group in a sugar in what we call a glycosidic linkage. All right, so let me show you an example of a glycosidic linkage. All right, so let's say you have a sugar. All right, as you'll see in chapter 16, these are frequently 5 or 6 membered rings. And they have lots of OHs sticking up and around, all right? So what you're going to have is you're going to have an O that's linking your sugar ring and your fatty acid. This right here is the glycosidic linkage. All right. Actually, I made an error there. Let me fix something. Usually there's not a carbonyl group. Usually it's arranged so that the carbonyl group is not part of that. Then it's not a glycosidic linkage anymore. So that would be that's an R. I read that really thick. Didn't mean to. But you get the idea. So basically it's kind of an ether linkage. Involving a sugar. And I just dropped my Apple Pencil. There we go. Okay. And there's several different types. You know, you can have oodles and boodles of different types of glycolipids, depending on what else is present within the molecule. All right. I do want to highlight the one here. If you can't see it that well in the video, look at it in your PowerPoint or the book. In the book is on page 198, figure 8.7, and also you can see it, of course, in this show. I want to highlight this because this structure is incorrect. The book made a mistake here. Can you guys tell what the mistake is? Give you a second to find it. It is missing an oxygen. Sorry for the lawnmower in my background. They're mowing outside my office window. Here's what that picture should look like. All right. So that's what the picture should look like, figure 8.7. They forgot to put this guy in there. That's important. Always got to have that linking O whenever you have a glycosidic linkage. All right. And so again, you can have several different types there. Specifically, if you have one that's a derivative of a ceramide, those are called cerebrosides. Although they're not all, they don't have to be. You can have glycolipids that are not derived from ceramides, but if they are, they're called cerebrosides. And then you can have a particular type of cerebroside called a ganglioside. These have at least 3 saccharides present within your sugar unit, right? So, yeah, your sugar unit doesn't just have to be one sugar ring. You can have actually a saccharide chain. So, like in this case, there's 4 of them. There's D-galactose, N-acetyl D-galactosamine, D-galactose, and then one called sialic acid. Gangliosides always have at least 1 sialic acid in there. All right. Whew. That's the end of the first category of lipids. There's a lot of them, as you can see. Fortunately, the second group isn't nearly... It's got a lot of components, but they are much more closely related and less varied in terms of family than the ones we saw. The second group is steroids, basically. And of course, you've heard of steroids in different contexts. These are different structurally. These do not have the polar head group hydrophobic tail like fatty acids and other related compounds. These have big fused ring structures, and they tend to have 4 rings, 3 6-membered rings and 1 5-membered ring. All right. Probably the most well-known example of a steroid is cholesterol, and I'm sure everybody has heard of that. Cholesterol is shown in this picture. You see in part A, they have sort of the generic ring structure, and you can see that several of these representative steroids are using that base ring structure. They just have slight derivations to fit the purposes. Cholesterol is a really prominent one. The secondary sex hormones, like your testosterone, estradiol, progesterone, these are all types of steroids, and you can see those listed there. A lot of times when people think steroids, they automatically think of what we call anabolic steroids. And yeah, anabolic steroids do have this common ring structure, but just because you have that structure doesn't mean it's anabolic. Anabolic means that you're using it to build up sort of muscle tissue and other metabolic products. There are several other types of steroids that have different functions. Glucocorticoids is another example. These are used specifically to decrease inflammation. If you have muscle issues like tears or something, sometimes you'll get a prescription for a glucocorticoid to help reduce the inflammation and the pain. You have mineralocorticoids. These are meant to maintain salt and water balance in the body. And of course, as we mentioned, you have your secondary sex hormones that are also steroid-based. Okay, deep breath. I think we're going to stop this video here. That's a lot to digest. And I will come back with the second half of the chapter in a later video. All right? Till then, talk to you soon. Bye-bye.